Right. So in the last class, I introduced this definition of pack learning, which is the following. So hypothesis class is said to be pack learnable if for every epsilon and delta greater than 0, I can achieve this epsilon delta error, which is that with probability at least 1 minus delta, there's a learning algorithm that achieves a generalization error that is epsilon close to the best possible generalization error that I can achieve within the class. All right. And I can achieve this using a finite number of samples. In particular, there is some n of epsilon comma delta such that if I have at least those many samples, irrespective of what is the underlying distribution, right? So this n of epsilon comma delta does not depend on the underlying ground truth distribution. That's something to be kept in mind, right? So for every distribution, there is some n of epsilon comma delta, which depends on epsilon and delta alone, and implicitly this depends on the hypothesis class and the loss function, but that's it. So if I can achieve this epsilon delta error using at least, as long as the number of samples is at least n of epsilon comma delta for some finite n of epsilon comma delta, then we say that this hypothesis class is pack learnable, right? And this is, if you think about it, this is kind of the basic requirement that we would demand. Of course, all of this is under the specific supervised learning model that we have seen so far, right? So under that probabilistic model, where we have a training data set which is drawn IID according to PXY, and it is going to be tested on a sample or another test data set, again drawn according to the same distribution but independent of the training data set. Under that specific model, this is kind of the minimum that we would expect, right? This is the best that we can hope for. So the question is, let's say that there is some learning algorithm which can do this. Is there one general learning algorithm that will allow me to learn a particular hypothesis class that is pack learnable? And can we do it efficiently, right? Is there a computationally efficient way of finding a HS that satisfies this particular property? Now, leaving the computational complexity aside, it turns out that it is possible to do so, and that was using this idea called empirical risk minimization. Again, I introduced empirical risk minimization in the context of learning finite hypothesis classes. Right? In particular, H, the script H, the set of all functions that from which I want to learn, is only finite. Right? But it turns out that this holds more generally. So whenever you're posed with a supervised learning problem, what you should ideally do is, or the first thing to start with is find that particular predictor that minimizes the empirical risk. Right? So this particular quantity is called the empirical risk, and I'll maybe call it RS or RS hat of H. So in general, whenever I put a hat, it will typically denote some kind of an empirical quantity or an estimate. And I'll introduce this subscript just to denote that this depends on the data set. Okay, so you choose that H which minimizes the empirical risk RS hat of H. And it turns out that this suffices, irrespective of what the hypothesis class is, as long as it is finite. And in fact, as long as the loss function is sufficiently nice, it doesn't even have to be a binary classification problem. It can be any supervised learning problem with sort of regular L. If you want something concrete, you can assume that the loss function L is bounded between two numbers. Doesn't matter what those two bounds are, but as long as the loss function is bounded, ERM can allow you to learn. So there is, using a finite number of samples, you can achieve arbitrarily small epsilon delta error. All right. But then we also saw a negative result that not all hypothesis classes are pack learnable. There are some hypothesis classes which cannot be learned. In particular, if the size of the feature space is infinite and H is the set of all possible functions, then this is not pack learnable. So if I use ERM or any other learning algorithm, I cannot achieve an arbitrarily small epsilon comma delta L. Right? So we have these two extremes. In one case, if you have finitely many H in your hypothesis class, then it is learnable. We know that, and we have an explicit learning algorithm, which is ERM. At the other end,
So
if the
I
feature
have a
space is
question here.
infinite and H is the set of all possible functions, then this is not pack learnable. And in fact, here, the feature space, it's enough if it is just countably infinite. It doesn't even have to be uncountably infinite. Right? So what happens in between? So clearly, there are some hypothesis classes which are not pack learnable, and there are some hypothesis classes that are pack learnable. And neither of these two extremes that I have presented over here are particularly interesting, because we don't want to learn from the set of all possible functions. We're happy to restrict ourselves to, let's say, polynomial classifiers or neural networks or linear classifiers, right? And all these three examples that I mentioned over here, they don't fall into either of these two categories, right? It's not the setup. So H is not the set of all possible functions. The cardinality of X is infinite in all these three examples that I presented: polynomial classifier, linear classifier, as well as neural networks. Typically, the inputs are real vectors, which means that the feature space is infinite. It's uncountably infinite. H is some restricted class of functions, but you don't have finitely many. There are infinitely many functions, right? Because you have infinitely many polynomials of degree k. And there are infinitely many linear classifiers, because you can choose the hyperplane or the coefficients corresponding to the hyperplane as you want. They're all real values. Right? So when can we say that a particular hypothesis class is pack learnable? Because if it is not pack learnable, then there's little that you can do. There's no point in even searching for a good learning algorithm, at least not yet. All right. So what about infinite hypothesis classes, which are really the interesting category of hypothesis classes? It turns out that depending on what your learning problem is, whether it's a classification problem, whether it's a regression problem, or whether it's binary classification or multi-class classification, the answer can change. And for each of these problems, the learnability is determined by some combinatorial measure of complexity. So intuitively, the more complex a hypothesis class is, the more difficult it should be to learn. So for example, if loosely speaking, if I take, say, polynomial classifiers, so all polynomials of degree k, of degree 10 versus all polynomials of degree 100, which one do you think is more difficult to learn? Polynomials of degree 100, right? At most 100. That should be more difficult to learn, because within the same, they all belong to the same family of classifiers. But in one case, there are more parameters to learn. In the other case, there are fewer parameters to learn. So if there are fewer parameters to learn, then hopefully it should be easier to learn. And hopefully you need fewer number of samples. Right? And in this particular example, one is a strict subset of the other. So that should tell you that if you have a subset of functions among which you want to learn, then it should be easy. So the measure of complexity that determines whether a particular hypothesis class is pack learnable or not depends on the supervised learning problem. And again, we will not go into too much detail, but for binary classification, it turns out that the quantity of interest that determines whether the class is pack learnable or not is something called the VC dimension. For multi-class classification, there's no one single quantity that determines this, but two parameters which sort of tell you whether something is pack learnable or not are the ds dimension and the Natarajan dimension. These are two different combinatorial quantities. And for regression, so one parameter that is used, a very popular parameter, is called the fat shattering dimension. Again, these are not the only parameters. There are other parameters that also allow you to say whether a particular hypothesis class is pack learnable or not. And in addition, also give you bounds on the sample complexity in terms of these parameters. So if you know, let's say, the VC dimension of your hypothesis class, then you can A, say whether it's pack learnable or not, and B, also give bounds on the sample complexity. Right? So it gives you a lot more information than just whether it is pack learnable or not. It also tells you how many samples do you need in order to achieve a certain epsilon delta error. All right. So we'll look at VC dimension in a little more detail, but we won't really talk about these other quantities. All right. So the VC dimension, also the Vapnik Chervonenkis dimension. So this is one parameter which tells you whether a binary classification problem is pack learnable or not. So let me define the VC dimension and then say what it tells you about whether the hypothesis class is learnable or not. So loosely speaking, again, if we take a step back and try to think about the problem intuitively, when do you think a particular hypothesis class is not pack learnable? Ideally, it's not pack learnable if it is too rich. That's what I said, right? And one way of measuring richness is how many possible labelings can I generate for a given set of points. So let's say I have n samples. Is it possible to generate all possible labelings for those n points? If I take binary classification and there are n points in my data set, then how many possible ways, theoretically, what is the maximum number of ways I can label these n points? It's the power n, right? Because for each point or each feature, I can label it in two different ways, either +1 or 0, right? So there are 2 to the n possible labelings. And suppose I look at the set of all possible functions. Then for every set of n points, I can generate all possible labelings by definition, because I have all possible functions at my disposal. If I don't have too many functions, and after some point, I'll not be able to generate all possible labelings. If I have too many samples, then the number of possible labelings won't be too many. So if I collect more and more samples, the number of functions, that number of possible labelings I can generate reduces. So hopefully, if I collect more samples, it should be easier to identify what the right function is. If not, there's no hope, right? Because then I'll be confused as to what the correct labeling of these endpoints are, because there are many functions to choose from, right? So we say that a set of, say, m points is said to be shattered by the hypothesis class if for every labeling I can find a predictor h such that that predictor gives me that particular labeling, right? That labeling for all of these m points. So I have m possible points, let's say 4 possible points. I should be able to find for every labeling, let's say I label this 0, 1, 1, 0. For this labeling, I should be able to generate this labeling using some function from h. I take another labeling, I should be able to find some other function that gives me this particular labeling for those 4 points, and so on. Right? If using the functions from h, I can generate all possible 2 to the m labelings of these m points, then I say that this set is shattered by the hypothesis class. Okay. So shattering basically means I can generate all possible labelings using the functions from my class. Any questions? Great. So clearly, if I can always shatter every subset, then it's impossible to learn, right? Ideally, at least intuitively, it feels like the hypothesis class is very rich. On the other hand, if it is not possible to shatter every set, then the hypothesis class is not too rich. I'm just trying to build intuition over here, nothing formal, right? Because if there are different ways of labeling a particular subset of points, then there's then it's you get more confused. The learning algorithm gets more confused as to what the true labeling should be. Okay, that's sort of the intuition you should have in mind. So the VC dimension of H is the size of the largest subset of X that can be shattered by H. All right. So in particular, this means two things. So if the VC dimension of a hypothesis class is equal to some number, let's say D, then it means two things. One, there is some subset of D points, let's say x1, x2 up to xd, which is shattered by H. So in other words, if I look at the following, I look at f of, let's say, h of x1, h of x2, up to h of xd. You pick, so I have d points. I take every function in my hypothesis class and apply it to all of these d points. So for every h, I get a d tuple of labelings. Right? For one particular h, I maybe get a labeling 0, 0, 1, 1, 1. For another h, I get maybe 1, 0, 1, 0, 1, 0. Right? So I look at all possible labelings and see how many unique labelings I get. The number of such unique labelings is 2 to the power d, which is the maximum possible, which means I can generate all possible labelings, then it is shattered. And this set of d points is shattered. So if the VC dimension is equal to d, then there are d points. There exists some set of d points which is shattered by H. And it also means that if I take any d plus 1 points, no matter how I choose these d plus 1 points, these will not be shattered by H. Any questions? So one thing to note is that this first statement doesn't mean that every set of d points is shattered. It means that there is some set of d points which is shattered by H. Okay. Just to let's think about which one? So this set X could be continuous. So these are just vectors from X. That's it. So it's a finite set. Right? This is find some finite subset of X.
In the second one also,
it's again finite. Everything is finite, right?
Like we can the vectors in first one could be like will be contained in second one.
Maybe so. In the second case, it doesn't matter how I choose these d+1 points, right? They cannot be shattered by H. So in particular, let's say that I have one set over here which is shattered by H. I cannot, if I add another point to this set, no matter how I choose the next point, the d+1 point, it will not be shattered. Right.
With the same set.
It
That's
could
one
be, but
vector.
it need not
That's
be.
one vector.
Yes, it could be, but it need not be also. Correct. You cannot get 2 to the power d+1 unique labels. Right. So let's look at some. Again, let's go back to the two extreme examples that we've seen so far. In one case, the set of all possible functions. In the second case, finitely many functions. So suppose that H, let's assume that the cardinality of X is infinite and H is set of all functions. Then what can you say about the VC dimension?
Some finite set can be shattered.
Some finite set, or again, can you give me a number for the VC dimension of H? Is it 2, 3, 10, 100? What would it be? Infinite. And why? All possible functions. So let's say I take any subset of points, right? So take any x1 up to xn. So take any set of points. Since H is the set of all possible functions, for every configuration of zeros and ones, I can find one such H that gives me that particular configuration. In particular, I can generate all 2 to the m configurations. And I can do this for every m because H is the set of all functions and the cardinality of X is infinite. So I can find I can find m distinct points from X. Right. So the VC dimension of H is infinite. Any questions?
If there are infinite points, it will still be shattered, is
I
it?
can do this for m+1, m+2, m+3, and so on, right? For everything, all of them are shattered. I'm sorry?
Okay.
So it is not pack learnable, right? Because we've seen earlier through the no free lunch theorem that this particular hypothesis class is not pack learnable. So let's see the other extreme example where again, let's assume that the cardinality of X is is infinite, doesn't matter. It could be finite, it could be infinite, doesn't matter. And H has say H1 up to Hk. There are k functions in H. All right. What can you say about the VC dimension of H? Why?
So if we take K,
Mhm.
we take this two point, for any 2 point labels, we can try to take the hypothesis class.
Okay, think about it. It is not K. I mean, K is a very, very loose upper bound. No. Okay, so here's a hint which almost answers the question. Using K functions, how many distinct configurations can I generate? How many distinct labels can you generate? I mean, there are K distinct labels that I can generate, right? No more than K. Right. So let's say if is it, let's say I have 3 functions in my hypothesis class, all right? And I take any 2 points, x1, x2. Is it possible to generate 4 distinct labelings of these 2 points using 3 functions? You can't, because there are only 3 functions. So there are only 3 distinct configurations that I can at most 3 distinct configurations that I can possibly choose. This essentially just follows from the pigeonhole principle, right? So the VC dimension, so the number of distinct configurations I can generate is K. So therefore, what should be the VC dimension? So it's at most CL of log K to the base 2. Because the number of configurations for m points is 2 to the m. So 2 to the m obviously has to be less than or equal to K. So m has to be less than or equal to log K. In fact, it's strict, yeah, it's less than or equal to log K. Any questions? So in these 2 extremes, in the first case, the VC dimension is infinite. In the second case, the VC dimension is log K to the base 2, which is finite. And we know that the second case, it is pack learnable. In the first case, it is not pack learnable. And in fact, there's a much more general result. Again, something that we won't prove in this course, that H, again, I'm implicitly assuming that this is a binary classification problem. So for a binary classification problem, implicitly the 0-1 loss, H is pack learnable. If and only if the VC dimension is finite. All right. So let's see a couple of simple examples. So far we've seen only 2 extreme examples, set of all possible functions and finitely many functions. Right? Let's now see let's see some examples of hypothesis classes that have infinitely many functions, but we'll also see whether these are pack learnable or not. All right, so let's see another example. Suppose that X, the feature space, is the set of all real numbers. Y is 0, 1, so it's a binary classification problem. And H is the set of all threshold functions. So H of X is 1 if A is less than or equal to X and 0 otherwise, for all possible A. So this consists of all possible step functions. Right. So how do you find the VC dimension of this particular set? Let's start from 1, right? So take any point X. So there's only one point, some number. Can this set be shattered? Right? Which means that for this point, I should be able to, there is some function which gives me the label 0, and there's some function which gives me the label 1. Can I shatter this set? It is. Why? How do I choose the two? Correct. All right, to get 0, basically, I just have to choose A, which is less than, sorry, I should choose A, which is greater than x1. And to get 1, I can choose any A that is less than x1. So if I have some x1, if I choose an A which is less than x1, then h of x1 is 1. And if I choose an A which is greater than x1, then h of x1 is 0. Right? Now let's look at 2 points. So the first line of argument, it tells us that the VC dimension is at least 1. Doesn't mean that it's equal to 1. Let's take 2 points. For now, I'll assume that x1 is less than x2. I can do that without any loss of generality. Can this set be shattered? Why? Correct. So it's impossible to get 1, 0. Right? Because if h of x1 is 1, then every point to the right of x1 should be labeled 1. Because these threshold functions are, once they become 1, they're equal to 1 from that point onwards. Right? So this cannot be shattered. Since there's no h for which h of x1 equal to 1 and h of x2 is equal to 0, again assuming that x1 is less than x2. And it doesn't matter how you choose x1 and x2, as long as they're distinct, it is not possible to shatter them. So this is an example of a hypothesis class which has finite VC dimension. It has VC dimension of 1, and therefore it is pack learnable. Right? So I'll leave it the rest of these as an exercise for you. Again, find the VC dimension of this particular hypothesis class, which is all functions which sort of look like this. There's an A, there's a B. It labels everything between A and B 1, and everything outside A comma B is 0. And this is an example that we saw previously in the previous class. Right? And probably the more interesting hypothesis class is the perceptron, or the linear classifier. In fact, I'll give you what the VC dimension should be. In this case, the VC dimension is equal to 2. And in this case, the VC dimension is equal to 3. In general, for if A is in RD, let's assume that X, the feature space, is RD. So for this hypothesis class, the VC dimension is exactly equal to D plus 1. This is a little harder to prove, but I still would like you to think about it. These three are in very small dimensions, so it's very easy to visualize and prove this. In general, the easy part is showing that the VC dimension is at least D. That is, you have to find a set of M points or D points which can be shattered. The harder part is to show that any set of D plus 1 points cannot be shattered, because you have to show it for every set of D plus 1 points, not just for one arbitrary set of points. Right? But at least for the perceptron, you can try to prove the lower bound, if not the upper bound. So in the examples, we've seen just these few examples. In some sense, the VC dimension depends on the number of free parameters. So all of these are described using parameters A comma B, or vector A and B. Right? And here there was one free parameter and the VC dimension happened to be 1. In this case, there were two free parameters and therefore the VC dimension happened to be 2. In this case, there are 3, and more generally D plus 1 free parameters, and the VC dimension happens to be D plus 1. But this can lead you to think that the VC dimension is proportional to the number of free parameters, which is not necessarily the case. All right. So if you have a family of functions or family of hypothesis classes which are parameterized by some number of parameters, for example, polynomials of degree k, then the VC dimension of this family is proportional to k. But then there can also be hypothesis classes which have only one free parameter but have infinite VC dimension. And here is one such example. It's an interesting exercise to show that the VC dimension of this hypothesis class is infinite. So there's only one free parameter, and its indicator And the function is of the form indicator sine ax greater than or equal to 0. So every function from this hypothesis class is some sinusoidal function. It extends on both sides. The only parameter that differs is the frequency. The amplitude remains the same. You can only change the frequency of the sine wave, and everything. So all x for which sine ax is greater than or equal to 0 is labeled 1. So essentially, every x that lies in this interval or this interval or this interval or this, so these are labeled +1, and outside the orange intervals it's labeled 0. Okay, it seems like a very simple hypothesis class, and it's a little bit counterintuitive as to why the hypothesis class should have infinite VC dimension, but still try to think about it. So as I said earlier, the VC dimension of a hypothesis class tells you whether it is pack learnable or not. So if it has finite VC dimension, then it is pack learnable. If it has infinite VC dimension, then it is not pack learnable. But you can say something more. You can also bound the sample complexity in terms of the VC dimension. And in fact, you can show that the sample complexity is up to a multiplicative constant equal to the VC dimension plus log 1 over delta divided by epsilon square for some universal constants C1 and C2. All right. So loosely speaking, the sample complexity of a hypothesis class is proportional to the VC dimension. All right. If we go back to, let's say, the concrete example of the linear classifier, it means that, so what does the sample complexity tell us? The sample complexity tells us that you need at least these many samples in order to get a particular epsilon and delta F. Right? And if you increase the number of samples, then you can possibly get a smaller epsilon and delta F. But this particular statement concretely tells us how many samples we would need to achieve a particular epsilon and delta error for linear classifiers. Because the VC dimension was equal to d plus 1, where d is the ambient dimension, this tells us that the number of samples that you need is proportional to d. Right? It's not exponential in d, it's not logarithmic in d, but it is proportional to d. So if somehow, in many cases, it is not easy to compute the VC dimension, but if, let's say, you have a bound on the VC dimension of a hypothesis class, let's say neural networks, single layer or two layer neural networks, then you can also tell how many samples you need in order to learn that particular hypothesis class. So this can be very useful, at least a rough, even if you can give loose bounds on the VC dimension, or even say, how does the VC dimension scale with the number of parameters, then it can be very, very helpful. Because it tells you that, let's say I have 1 million samples in my data set, then what is the size of the largest neural network that I can train? If the size of the neural network is too large, then at least this learning theoretic ideas tell us that you need at least these many samples. You cannot achieve an arbitrarily small epsilon delta error. If I'm training a linear classifier and the number of samples that I have is much smaller than d plus log 1 over delta by epsilon square, then it means that I can't really achieve a small error, a small generalization error. Right? So if you want to achieve a small generalization error, then the number of samples, how many samples you need, is determined by the sample complexity, which you get to know something about that from the VC dimension. All right. Okay. So this obviously means that if you have two different hypothesis classes, then if the hypothesis class has a smaller VC dimension, then it is easier to train because the sample complexity is lower. In the end, you're always limited in terms of the amount of data that is available to you. You don't have an infinite amount of data. So given that you have, let's say, 1,000,000 data points, what is the largest or most complex hypothesis class that you can possibly train using these 1,000,000 samples? That's the high level question that we want to address. All right. But then it also leads to more complicated problems. For example, let's take the set of polynomial classifiers, right? Or okay, this should have been indicator summation ai x power I greater than or equal to 0. All right, let's look at the class of polynomial classifiers of degree at most m. Right. Now, how do you choose m? One way is to find the VC dimension of this particular hypothesis class, right? And then using the VC dimension and given the number of samples, you choose the degree m. Choose it so that you have the number of samples that you have is at least the sample complexity. That is one particular approach of solving this particular problem, of choosing h. And a larger m means that you can approximate the true function closely. That is, you can achieve a small approximation error. But a smaller m means that it can also be learned more easily. So you can achieve a small estimation error, right? But then it turns out that there's a more principled approach for choosing the hypothesis class. In this case, this m is sort of a free parameter that you're allowed to choose. I'm restricting myself to polynomial classifiers, right? It's a family of classifiers, or it's a family of hypothesis classes where this m can be chosen. Larger m means it's more complex. Smaller m means it's simpler. So m equal to 1 gives me linear classifier. M larger than 1 gives me higher degree polynomial classifiers. Right? So in statistical learning theory, there is this notion of structural risk minimization, which minimizes not the empirical risk directly, but rather the empirical risk plus some measure of complexity of the hypothesis class. So instead of directly minimizing the empirical risk, you add another penalty term, which says that, okay, choose a higher degree polynomial, but then you also add a penalty for choosing the higher degree polynomial. Right? For example, if I give you, say, n points, then a polynomial of degree n can give you 0 training error. Right? So this empirical risk would be exactly equal to 0. So if I took the set of all possible polynomial classifiers, then there wouldn't be much to do. But then if I also add a penalty term which says that if m is larger, then you penalize it more, then at some point you stop, right? Because this penalty term becomes large. So then there's a delicate balance between the degree of the polynomial and the empirical risk that it can achieve. So there's a very principled way of choosing this particular measure of complexity, but unfortunately, it's not computationally efficient to do so. So this quantity over here is called the Rademacher complexity. And this is a very high level idea that is extended beyond this structural risk minimization. So one way of interpreting this is that instead of just doing simple empirical risk minimization, you add a so-called regularization term that penalizes more complex classifiers. Essentially, the setup is the following. You have a family of hypothesis classes, and you want to have a delicate balance between the approximation error and the estimation error. The smaller m means that you can achieve a lower estimation error but a higher approximation error. Larger m, so m, so if m is large, that is the degree of the polynomial is large, then the approximation error is lower because you can approximate a richer class of functions. But the estimation error is higher because the VC dimension is large, and also it's harder to, you need more number of samples in order to get the same generalization error. On the other hand, if you take a small m, then the approximation error is large, but the estimation error is small. Right? And this one way of balancing this out is by penalizing. So you have to penalize large m, very large m. But then you shouldn't choose a very small m either. One way is to choose it in a very ad hoc fashion, but that doesn't help because you don't know what the generalization error will be, because all you have is your training data set. So if you choose this penalizing term or the regularization term to be the Rademacher complexity, then it turns out that you can again prove bounds on the generalization error even in this particular case. So even this family of polynomial classifiers can be learned efficiently. If you do just plain empirical risk minimization over the set of all possible polynomial classifiers, then there's no hope because you will overfit. Because there's always a polynomial of sufficiently high degree which will give you zero training error. And that's the fundamental problem. Right? So one way of avoiding overfitting is to choose such a regularization term. Now, this is a principled approach, but is unfortunately not computationally efficient. So people derive other regularization terms that give you good empirical performance with a little bit of theoretical backing. All right. So more generally, what you do in practice is you don't simply minimize the empirical risk, but you minimize the empirical risk plus a regularization term. And how you choose the regularization term depends on a lot of factors. It depends on exactly what problem you're trying to solve. And also if you have some information about the underlying ground truth. Right? So two very popular regularization terms are L1 regularization, where you replace this G of H is basically the L1 norm of the parameters. For example, if you're doing linear classification or linear regression, then the L1 regularization basically the penalty term is simply the L1 norm of H. And L2, this is basically the L2 norm of H, or sometimes the squared L2 norm of H. All right. And each of these give you different qualitative properties. If again, going back to the linear regression problem, L1 regularization promotes sparsity. It tries to ensure that the number of non-zero entries in the weight matrix or the weight vector is small. So it tries to force as many entries to zero as possible. On the other hand, L2 regularization has this property of improving the stability. By stability, I mean that if you make small changes to the data set, then the predictor doesn't change too much. Right? And that's a very important parameter, and that in fact you can prove that stable uh, learners don't overfit. So all of these are different approaches to avoid overfitting, and L2 regularization is by far one of the most popular approaches to avoid overfitting. All right. Any questions? Okay. So again, if we go back to the polynomial classifier problem, let's say that HM is the hypothesis class of polynomial classifiers of degree at most m. Right? As we've seen, the problem with large m is that you overfit. Right? But more generally, you can interpret in this particular form. Suppose that H is the hypothesis class of all possible polynomials, all possible polynomial classifiers. I can write this as a union of different polynomial classifiers. Okay, where each of these HM has finitely many trainable parameters. Because if you look at HM, you have polynomials of degree at most m. So there are m plus 1 free parameters or m plus 1 trainable parameters in your hypothesis class. But if the larger m you choose, the more number of free parameters you have. Right? So, but on the other hand, if you take the hypothesis class H itself, there are infinitely many trainable parameters. So I'm decomposing H into a bunch of families, and each family has finitely many trainable parameters. Okay. So this new parameter m, which you can choose, right? And this is such an m is sometimes called a hyperparameter. All right. For example, if you take a neural network, uh, let's say a feed-forward neural network, then the number of hidden neurons that you have could be a hyperparameter. Because the more number of hidden neurons you choose, the complexity of the hypothesis class increases. So the number of neurons is sometimes called the hyperparameter, and how you choose this hyperparameter is totally up to you, and it determines the hypothesis class that you choose. Right? Similarly, again, depending on the kind of hypothesis class that you choose. If you choose, say, a convolutional neural network, then the size of your convolutional kernel and many other, in general, you have a lot of these quantities that you want to choose, typically discretely. These are not trainable parameters, but you have to make discrete choices about the size of your hypothesis class. And this is typically a hyperparameter. So if you choose it arbitrarily, there are infinitely many ways to choose that from. And if you choose a large hyperparameter, then it leads to overfitting. So how do you balance the two? One approach is, of course, you do some kind of regularization. But even that doesn't necessarily help, because it's not easy to choose. It's not easy to do it computationally efficiently. So another approach is this approach of model selection. What you can do is you have your training set. So right now we're assuming that there's a training set and there's a testing set. All right. What you could potentially do is you split your training set or the number of samples that you have, n samples, into two parts, a training set and a validation set. Right? For each m, again, so I'm again going back to the polynomial classifier, but in general, for each choice of the hyperparameters, you find the ERM or the regularized ERM on the training set. Right? So I have, let's, again, for simplicity, let's assume that I have H1, H2, and H3. So I have, let's say I have three different choices for the hyperparameter. Right? Now I have a training set and a validation set. Note that this validation set is different from the testing set. Okay? Effectively, you're taking the training set itself and breaking it into two chunks. So you have a small number of validation samples. For each of these hyperparameters, you train using ERM or ARM with a regularizer. You get a H1, H2, H3, and so on. For each choice of the hyperparameter, you get a different ERM. If you think about it in terms of the polynomial classifier example, then using the training set, you find the best possible polynomial classifier of degree 1, the best possible polynomial classifier of degree 2, best possible polynomial classifier of degree 3, and so on, up to how much ever you can do. Right? Now, for each of these, you evaluate the best degree 1 polynomial classifier on the validation set. Again, you find the performance of each of these on the validation set. So let me call this HERM1, HERM2, HERM3. So all of these are trained on the same set of samples. That's something to be kept in mind. And then you find the empirical risk of each of these. And out of these, you choose the best possible one. So you choose that M which does the best on the validation set. All right. So this principle is used irrespective of whether you're doing deep learning or some standard machine learning, right? And there's a specific reason why you're doing so. So if you think about it intuitively, all right, what would happen? Suppose that, again, forget about computational complexity, but let's say we're trying to learn a polynomial classifier. Beyond a certain point, the polynomial classifier would give you zero training error, because if you increase the degree of the polynomial, it will overfit, right? So as you go down, the training error is definitely going to decrease. But remember, our goal is not to minimize the training error, it's to minimize the generalization error. So this validation set is sort of a proxy of the generalization error. So we don't have the test set itself, but we're using this validation to check the performance of the training. We're sort of simulating the testing using this validation set. So even though the training error keeps decreasing as you go from H1 to H2 to H3 and so on, that doesn't happen in the case of the validation error. Because typically what you would see is that the validation error would maybe decrease as you increase M, but then it will again increase. Because maybe the ground truth is a polynomial of degree 10. Right? So the generalization error would be minimum among polynomials of degree 10. But then if you chose a higher degree polynomial, then again you have it overfits, so you're not sure how to choose. So the generalization error would potentially increase. So validation is one way of choosing the model or choosing the hyperparameters in your learning problem. All right, so you choose that HM that gives you the lowest empirical risk on the validation set. So in general, this is sort of a very general framework for choosing hyperparameters. And one thing to keep in mind is that you don't choose the hyperparameters based on the performance of your final test set. It's done using the validation set, which is kept separate from the test set. Never mix the two. I mean, if you choose your hyperparameters based on how well it performs on your test set, then it means that whatever results that you get from your test set are not valid anymore. Right? So that's one thing you should always keep in mind. The test set is sacred. You don't make any decisions of choosing hyperparameters or choosing your learning algorithm based on the test set. All right? Great. So this approach that I outlined here, it requires a separate validation set. So you have n samples. Let's say you have a million samples. Now you have to split it into two parts. Maybe I use, say, 10,000 samples for my validation set and the remaining for my training set. But this means that I now have lost some of the training samples for validation. And that can potentially be challenging when the number of samples that you have is not too large. So an alternate approach is this idea called k-fold cross-validation, where you do the following. So you take the training set and you partition it into k folds or subsets of equal size. All right. So for a fixed hyperparameter, you do ERM on all of them except one particular fold, and then you average. All right. So basically, I have my training set. I split it into k parts. All right. And let's say I leave out this particular fold and then find the ERM for. So for ERM, you take these samples. So using these samples, you find the ERM and then look at the performance on this particular fold. And then you repeat over other folds. So for the next, you find the ERM using these samples and evaluate the performance on this particular fold. And then you average over all possible folds. Right? So that's called k-fold cross-validation. And people take that to an even more extreme, where you take k to be equal to n. So in other words, you train using all but one sample, and then use that one sample as the fold over which you evaluate. And then you average over all possible folds. Right? So in each of these cases, you can potentially get a different ERM, right? So basically what you would do is, in this case, for the same hyperparameter theta, you get a H1 theta, you get a H2 theta, and so on. So you have k folds, So you have h1 theta, h2 theta up to hk theta. All of these were trained using ERM for the same hyperparameter choice theta. And then you evaluate the performance. So the loss of each of these. Now this loss is computed on these samples. This loss is computed on these samples and so on. And then you average. And you do that for different choices of theta. The theta that minimizes this average loss is going to be finally chosen. All right. So that is k-fold cross-validation. So now you know that if you're given a particular supervised learning problem, it could be classification or it could be regression, you now have a rough idea of what to do. Right? You do ERM or some regularized ERM. If your hypothesis class is too rich, then you try to break it up into simpler hypothesis classes, and you choose the hyperparameter using some form of model selection, maybe using cross-validation, k-fold cross-validation. But then how do you do ERM itself? Because in many cases, doing the ERM is not computationally easy. In regression with squared error loss, it's fairly simple. But then even if you look at the simple binary classification problem with 0-1 loss, it turns out that for a general hypothesis class, finding the ERM is NP hard. So there's no efficient algorithm that will let you find the ERM, because this 0-1 loss it's not smooth, right? So the general approach is to choose a different loss function. You want to evaluate with respect to the 0-1 loss. The end goal is to design a classifier that minimizes the 0-1 loss. But then at the time of training, you choose a different loss called the surrogate loss. So instead of doing ERM using the original loss, you do ERM using this surrogate loss. All right. And the surrogate loss is chosen so that it at least closely approximates the original loss, which is your 0-1 loss. But at the same time, there is some algorithm which allows you to minimize this surrogate loss efficiently. So we want this surrogate to be close to the original loss function, but also have some nice properties, maybe convexity, maybe smoothness, and so on. All right. So again, taking a step back, if we have to put everything that we've seen so far into a recipe, right? What do? You're given a hypothesis class, which could be, say, linear classifiers or polynomial classifiers or neural network classifiers. You're given a training set, and maybe you split it into training and validation. And then you have a final test set over which you want to evaluate, right? So the typical, if your original loss function is nice enough, then fine, you can go ahead. But then if it is not nice, if it's, say, the 0-1 loss, then you replace that with some convex, maybe smooth surrogate loss function L prime. In the case of binary classification, one very common loss that is used is the cross entropy loss. We'll investigate that in a little more detail, but that's the cross entropy loss is one classic example of a surrogate loss function. And then, having chosen this, you choose a regularization term and then minimize and then find the approximate ERM. Right. So now there are different approximations or different sources of error that are being introduced. Right. So originally we wanted to do ERM on a particular loss function, but now instead of doing ERM, we are doing ERM with a regularizer. Plus, we are also replacing the loss function with a surrogate loss function. But even then, it's not easy to find the the minimizer efficiently. So you do this minimization also approximately. And this is typically done using some kind of a gradient descent type of approach. Right? So this whole set of approximations, right? Let me combine all of these put together. This also introduces an additional error. This brings an additional source of error called the optimization error. So originally what you wanted to do was ERM over the original loss function. You're not able to do that because there's no computationally efficient algorithm to do so. So instead, you resort to a series of approximations. One is you approximate the loss function. The second, you introduce a regularization term. And the third, you do the minimization itself approximately using some kind of a gradient descent type of algorithm. And then additionally, if you have hyperparameters that you need to choose from, then you tune the hyperparameters using your validation set, or you just do some k-fold cross-validation. And once you do this, you estimate the generalization error using your test set. But one thing to keep in mind is that although you're training using the surrogate loss function, when you do the testing, it is always done using the original loss function. So if you're doing binary, or if you're doing a classification problem, you will minimize the cross entropy loss at the time of training. But then when you report, you typically report the probability of error, or the number of false positives and the number of false negatives and so on. Okay, so that final testing is always with respect to the original loss function that you intended to minimize. All right. So this is sort of, this gives you a recipe for training any machine learning model, any supervised machine learning model. And in fact, many of these ideas also continue for other problems as well, not just supervised learning. In general, in most cases, you reformulate your learning problem into a corresponding optimization problem. And most optimization problems are going to be posed in this particular form. You minimize some average of functions plus some regularization term, where this whole minimizing this whole function itself could be complex, but then you approximate. All right. So we'll revisit all of these ideas as we go through the course. So far what I introduced was, maybe it was a bit fast because there were a lot of new concepts that came in. Maybe some of you were familiar with some of these concepts or had seen this in some form in a previous course. But please go through these slides in a lot more detail so that you're comfortable with each and every idea. All of these have rigorous theoretical analysis, so that none of these are heuristic approaches. All right. But then, and we'll use each of these when we do training of deep learning and other machine learning models. But pretty much all of supervised learning follows the same recipe. The remaining magic or the art comes about in this particular part. How do you do optimization efficiently? The rest of it is typically fixed, and that part of the recipe is fixed. But then how do you do this approximate optimization? How do you choose the surrogate loss function? And something else, how do you choose the hypothesis class H, or the family of hypothesis classes, H1, H2, up to Hn? Right? So that's what we'll explore in a large part of this particular course. All right. There are a bunch of references provided over here, which you can go through. Most of this is based on this book by Shai Shalev Schwartz and Shai Ben David. There's a free PDF copy also available on the author website. And a link and details of this is also available in the course homepage. Right. So again, they were taken, all of this is scattered across multiple chapters of the book. So we've rushed through a lot of topics in a short amount of time. But if you want to learn more, including some of the details of the derivations, you can go through these particular chapters. Right? Any questions? Okay. So from the next class onwards, we'll try to unwrap this particular part. So how do you optimize? So far, we know we have a recipe of learning. We've taken care of the learning part. But then actually finding the empirical risk minimizer is something that we've not seen. How do we do this computationally efficiently? That's something that we'll briefly look at. And then we'll revisit optimization later on, once we've introduced some more concepts on how to choose the hypothesis class. All right. Okay, so we'll continue in the next class.